All right, I am picking up on page 6 of our packet on electricity, which is again from Greg Jacobs' 5 Steps to a 5. I'm looking at Kirchhoff's laws, conservation of charge, and energy. So there are two Kirchhoff's laws, the junction rule and the loop rule. Kirchhoff's junction rule says that the current entering a wire junction equals the current leaving the junction. This fact is a statement of conservation of charge. Since charge can't be created or destroyed, if 1 coulomb of charge enters a loop or a circuit each second, then the same amount must leave each second. Kirchhoff's loop rule says that the sum voltage changes around a loop. The sum of voltage changes around a circuit loop is 0. Well, I butchered saying that out loud, but what this is saying is that, like, the sum of delta V is 0 around a loop. This statement is a conservation of energy, because voltage is really just a different way of talking about energy. It's the change in the potential energy of 1 coulomb of charge. A battery can raise the potential energy of some charge that flows. A resistor will lower the potential energy of that charge. But the sum of all these energy changes must be 0. So in fact, our 4 key facts from before are actually just restatements of Kirchhoff's 2 laws. Let's look at that briefly. Let me find the page that has our 4 key facts. And I reformatted yours because one of mine got cut off. But the 4 key facts are that in a series circuit, series resistors must each carry the same current. That's a result of Kirchhoff's junction rule, because that's just saying that the current everywhere, if there's only one path for the current to take, and the current everywhere the current entering has to equal the current leaving, then it must be the same everywhere. The voltage across series resistors is different, but adds up to the total. That's a statement of the loop rule, because the total, if you have a 100-volt battery, and then each of your resistors is using part of it, those parts have to add up to the total from the battery. Then for parallel circuits, it's the voltage has to be the same across your resistors, and that's again from the loop rule, because each of those is its own loop, and each has to have the same. And then the current for parallel resistors has to add up, which is from the junction rule, because it says that the total current entering has to be the total current leaving, so if it's splitting off, those two have to add up. So these are overall ways. Oh no, that was a bell. That's in the recording. There's nothing I can do, I'm so sorry. I completely lost my train of thought. So these are just, Kirchhoff's laws are the 4 key facts, but they're in general terms of all circuits. The 4 key facts are restatements of Kirchhoff's laws, and thus of charge and energy, of conservation of charge and energy. The junction rule applies to facts about current, series resistors take the same current through each. Oh, I jumped the gun and went back to another page, but this is just saying that. Series resistors take the same current through each because there's no junction. The current through parallel resistors adds to the total because the junction before and after. Let me see if I can make words that make sense. Series resistors take the same current through each because there's no junction. There's no split. so it just has to be the same everywhere. The current through parallel resistors adds up to the total, because before and after the junction, it has to be the same, so it has to add up in between. The loop rule applies to facts about voltage. The voltage across series resistors adds up to the total because the resistors can only drop the potential energy as much as the battery raised the potential energy. Your resistors can't use more than 100 volts if your battery only provided 100 volts. The voltage across parallel resistors must be the same because Kirchhoff's loop rule applies to all the loops of a circuit. No matter which path you look at, the sum of the voltage change must still be 0. Power. Power is still defined as energy per second, just as it was when we talked about energy. Resistors generally convert electrical energy to other forms of energy. The amount of power says how quickly that conversion occurs. So, our formula here, to determine the power dissipated by a resistor, use the equation P equals IV. So power is current times voltage. However, using Ohm's law, which remember Ohm's law is V equals IR, so you can make P equals, if you plug in this for V, then you get I times IR, so P equals I squared R. And if you plug in for I, if you say like I equals, from Ohm's law, I equals V over R, you can say P equals, sorry, just realized you couldn't see. So if you plug in for V, you can change this as to P equals I squared R. If you plug in for, that's the bell again, if you plug in for I, you get V over R times V, so P equals V squared over R. So you basically have 3 different equations for power. However, let's see what the formula sheet gives you. The formula sheet only gives you P equals IV because the others are just plugging in this equation into that one. Tip from an AP physics veteran. If an AP question asks about power or equivalently the energy dissipated by a resistor per unit time, then just make a 4th column on your VIR chart. Use whichever of the power equations you can, whichever you have enough information for, to calculate power. Power does not obey the 4 key facts. The total power dissipated by a bunch of resistors is just the sum of the power dissipated by each, whether the resistors are in series, parallel, or whatever. So power isn't dependent on which type of circuit you're talking about. There's not any more math in the packet. The last page of your packet are some practice problems that I'm going to work. I don't know if I'm actually going to work them on video. There's a key to them in the 5 facts for the 5 book, but I'm also going to work a key, just so you have 2 different solutions, potentially. But the rest of this is more just talking about conceptual and potential questions you could see, which is maybe more useful. Alright, circuits from an experimental point of view. When a real circuit is set up in the laboratory, it usually consists of more than just resistors. Shocking, I know. Light bulbs and motors are 2 examples of things you commonly hook up to a battery other than a resistor. For computational purposes, however, we can pretty much consider any electronic device to act like a resistor, because they do basically the same thing. They use up voltage, they require a current. But if your purpose is not computation, if you're asked about observational or measurable effects, then you need to be able to talk about a light bulb as opposed to a resistor, because light bulbs, shockingly, light up. And you care about things like brightness and how you measure that. So let's talk about the brightness of the bulb. We talked about this a little bit when we talked about power before, because I talked about how power is actually a really terrible unit of brightness because it depends on the efficiency of your light bulb, but unfortunately it's still a thing. The brightness of the bulb depends solely on the power dissipated by the bulb. Power is given by any of the equations I squared R, IV, or V squared over R. You can remember from your own experience when you go to the store to buy a light bulb, you don't ask for a 400 ohm bulb, but for a 100 watt bulb. And a 100 watt bulb is brighter than a 20 watt bulb if you're talking about the same type of light bulb. But be careful, a bulb's power can change depending on the current and the voltage it's hooked up to. Consider this problem. A light bulb is rated at 100 watts in the United States, where standard wall outlet voltage is 120 volts. If this light bulb were plugged in Europe, where the standard wall outlet voltage is 240 volts, which of the following would be true? Your first instinct might be to say that because brightness depends on power, and the power is not changing, it's still a 100 watt bulb, then it would be exactly as bright, but it's not right. You can change the power of 100 watt bulbs. It's rated at 100 watts for our sockets. It's not rated as 100 watts for their sockets. Again, it's a terrible way to measure light bulbs, but we do it, and they ask us questions about it. So the actual answer here, I'm seeing if the answer is actually somewhere else. Nope, we have to actually think about it. So what you have to do is you have to look at your equations for power. P equals IV, P equals I squared R, and P equals V squared over R. Now, to know which of these we need to use to think about brightness, we need to know what does and doesn't change with voltage. And here's the deal. You can't use these two because current changes with voltage, and we don't know by how much. We don't know exactly how much changing this voltage is going to change the current, which makes these not appropriate. Resistance, look at this part down here. I know, I'm going slightly out of order. Under most operating conditions, the resistance of a light bulb is a property of the bulb itself and will not change no matter what the bulb is hooked to. So we could use this for something like the law of ones, because resistance isn't going to change. That's not strictly true. The resistance of a bulb can vary if it's very cold or very hot. However, unless the problem clearly states that you have to consider temperature variation, in which case it would have to give you some sort of rule for how to do that, you can assume that it stays constant. So if we use the law of ones here, oh, I wrote a R there, that's definitely a P. Get yourself together, Schneider. All right, so let's actually answer this. So voltage is doubling, resistance is not changing, and we're looking for how power changes. So voltage is doubling, resistance is not changing. The answer here is actually E, which is not a thing on AP tests. Shame on you, Greg Jacobs. The answer is E, that would be 4 times as bright. So when you're talking about, if you're asked about brightness, you have to think about power. You can assume, unless you're told otherwise, that resistance is going to stay the same, but voltage and current will change the amount of power, even for something that's called a 100 watt bulb. If you screwed a 100 watt bulb in Europe, it would be 400 watts. It would probably get super hot and potentially damage your lamp or whatever. So, bad news bears. All right, Ammeters. Alright, the other thing you have to worry about when you're talking about experimental values where you're talking about the experimental point of view for circuits is actually getting values for current and voltage, not just being given them in a problem. There are two types of meters you use, although what you actually use in a lab nowadays is called a multimeter, which takes the place of both of these. It has a knob you switch between the two. But there are ammeters and voltmeters. Ammeters measure current, voltmeters measure voltage. This should be pretty obvious since current is measured in amps, ammeters. Voltage is measured in volts, so voltmeters. It is not necessarily obvious, however, how to connect these to a circuit, and it is important because it's different for each. Not only is it important just in terms of doing well on the AP, it's also important in terms of if you hook an ammeter and particularly up the wrong way, you will destroy it, and it's bad. Even if it's multimeter, you'll still blow out the ammeter portion of it. So the way to think through this is not really to memorize it. You can, but that's not the point of AP Physics. It's to think through it. And what you have to remind yourself of is the properties of series and parallel resistors. So for resistors in parallel, voltage is the same. So if you're going to measure the voltage across a resistor, you want to get the same voltage, because basically the device becomes another resistor. And if you want to get the same number that's going through your existing resistors, you must put the voltmeter in parallel. L-L-E-L. In the following, it's not actually following, it's up here. In the figure, the meter labeled V2 measures the potential across the 100 ohm resistor because it's in parallel. It's creating a separate little path. While the meter labeled V1 measures the potential difference between points A and B, which is the voltage across R1 and the voltage across the combination of 2 and 3. And again, you had this was one little loop, this was another loop, and then this became its own loop. Because again, you just treat the meter as if it's its own resistor. And if you're measuring voltage, you want the resistance and you want the voltage to be the same, you need to attach them in parallel. Current is the same for any resistor in series with one another. So if you're measuring the current through a resistor, the ammeter must be in series. In the following figure, ammeter A1 measures the current through resistor 1, and they're in series with each other. There's no separate path. Current that goes through A1 will also go through R1, while ammeter A2 measures the current through resistor 2. Current's going this way. There's no separate path. If it goes through R2, it has to go through the ammeter 2. The reason that you'll blow something out is if you do this wrong is if you connect an ammeter in parallel. If you give it its own little path for the ammeter. Ammeters intentionally have super low resistance, and current, like water or anything else, takes the path of least resistance. So if you offer it this path with super low resistance, all of your current will try to go through there, and it's bad, and things inside of this delicate piece of machinery will be destroyed. Don't do it. As an exercise, ask yourself, is there a way to figure out the current in the other three resistors based only on the readings in these two ammeters? Okay, well, let's look at this. Kind of wish I hadn't drawn all over my picture, but that's okay. So this current, if you notice, this current has just left the battery. It hasn't had a chance to be split up into individual paths. So the current that goes through A1 is going to be the same as any other place where it's the total current. The current is splitting up here, if you notice. So A1 is not going to give us the current there, but we could use the value for A1 on R5 because all of the current has to come back together and go through here. So the same amount of current that went through here will have to go through here down at the bottom. For A2, we know that we had some total current that we measured with A1, it came here, it got split up, some of it went here and was measured by A2, some of it went over here, it went through these two resistors, and because R3 and R4 are in series with each other, they're going to have the same current. So to get the current between those two, we would do A1 minus A2. Because this is the total current, some of it's going here, some of it's going here. So the current here and the current here have to add up to this. So if we subtracted, we could find the current there. So the short answer is yes, you can find the current through all three of these resistors using those two readings, or all 5 resistors using the 2 readings that they've given us.